I'm Kristen Villalon. I'm a core scientist here at the EPIC SEM facility of Nuance.
Hi, and I'm Nick Gagola. I am an assistant core scientist at the EPIC SEM facility here at Nuance.
So our tech talk today is going to be about EDS detectors and how they work. We know that a lot of users here at Nuance use EDS, might even use it regularly and are maybe familiar already with how to analyze EDS data. But you might not know anything about actually how the detector works. How do we go from analyzing the X-rays from our sample to actually getting a spectrum on the computer? So hopefully you'll get a little bit more insight into the technique after the tech talk today. And if you don't know anything about EDS and want to learn more about how to actually do EDS, we'll include a link at the end of the talk so you can sign up for EDS training. And we'll also start off with a little bit of background for anyone who is unfamiliar with what EDS is and how it works. And then we'll get into talking about the EDS detector components, what they all are and what they do. And then we'll talk a little bit about the EDS detectors that we actually have equipped on some of our SEMs here at Nuance. So let's get into just some of the basic background. What is EDS? It stands for Energy Dispersive X-ray Spectroscopy. Often people call this EDS. You might also hear EDX. Both are totally valid. You might also hear EDAX, but this is actually a company that makes EDS detectors and software, but you can use EDS and EDX interchangeably. And so this is an SEM-based technique. So when you're imaging your sample, you have your primary electron beam hitting your sample. And when that primary beam hits your sample, it interacts with what we call an interaction volume. So a volume of material that electron beam is penetrating through, and it's going to cause a number of different processes to happen that release a number of different types of signals. Notably, the secondary electrons that are released are what we use for sort of our primary imaging mode in an SEM. It gives us topographical textural information. We also get backscattered electrons, which gives you compositional contrast. And then we have X-rays, which is sort of the topic of today. And those X-rays help us determine the chemical composition of our sample. And so to look a little more in detail about how exactly those signals are released, so the X-rays coming out of your sample kind of go hand in hand with the processes that release the secondary electrons and the backscattered electrons. So on the left here, we can look at a little animation of what's happening to generate secondary electrons. When we have our primary beam hitting our sample, we can knock out an inner shell electron from an atom in our sample. So we call those the secondary electrons because it's not from the primary beam, it comes from the sample itself. Now we have this vacancy and kind of a lower energy shell, and the other electrons really want that spot. It's sort of a better location than where they're at now. And so an electron will drop down from an outer shell and it will release an X-ray equivalent to the difference in energy between those two shells. Now we have this new vacancy here, and so the electron's going to go, I want to go there, and release another X-ray. And so we call these characteristic X-rays because these specific transitions are specific to the elements that they come from. So we can use them to characterize our sample. They're like kind of fingerprints for the elements that they come from. We have backscattered electrons, which is when our primary beam kind of reflects off the nucleus of an atom in our sample. And this is often an elastic process, but if it inelastically scatters, it might release an X-ray anywhere from sort of 0 to the total energy of the primary beam that you had. And so this is a continuum of X-ray energies being released from the sample. We call this Bremsstrahlung radiation. And both of these will eventually, if you're doing EDS, lead to a spectrum that looks like this, where you get these kind of narrow, tall peaks for the characteristic X-rays that help us ID our sample. And then you have this kind of low-level background, which comes from your Bremsstrahlung. So as you see with EDS, this is an X-ray detection technique. We're analyzing the X-rays that are being released from our sample. You might be aware of a number of other techniques that involve X-rays in different ways. This talk is specifically talking about EDS detectors. There might be a little bit of overlap with how the detectors and some of these other techniques work, but also maybe not. So just keep that in mind. We're specifically talking about not just X-ray detectors in general, EDS detectors specifically. So let's talk about the different detector components. So to talk about the EDS detector sort of depends on what you define as the detector. We can think of really the EDS detector assembly. What are all the hardware components that are involved when that X-ray is finally released from your sample, everything involved from converting that X-ray to your final spectrum you see on your computer. So we'll go into sort of all of these different components separately. Obviously, the detector part, sort of the main topic of today. It's the part really involved in sensing, detecting the X-rays, but even that detector is made up of its own components. And then there's all these other parts, cooling, the preamplifier, the pulse processor, and the multi-channel analyzer that are also really important to ultimately getting the data for your analysis. So I'll talk first about the detector. So the detector is made up of generally 4 parts. You have a collimator, which is a limiting aperture, and its purpose is to limit stray X-rays so that they don't get detected in your analysis. There's also the electron trap. You can kind of see in this diagram here, we're going in order from our collimator on the end, and then we have this electron trap just behind it. This is a pair of magnets that's going to deflect away any electrons that might try to make it into the detector. This will help reduce background, minimize artifacts, and also prevent damage on the sensor over time. The sensor is the sort of last thing we'll talk about. Then there's a window. There's also windowless detectors, but there's often a window behind the electron trap. This is a protective barrier or film between the final sensor crystal and the rest of the environment, and this will help mainly to prevent contamination on the crystal, also helps maintaining vacuum. And then we have the crystal, the sensor, kind of the literal detecting part of the detector. This is usually a silicon semiconductor that's going to interact with the X-rays. So let's look a little more closely at these last two, the window and the sensor, because when you hear about different types of detectors, it's often differences between these components. So there's 4 kind of main types of windows you might have in an EDS detector. You can have no window. And the benefit of having a windowless detector is that that film could potentially absorb low energy X-rays. And if you're interested in low Z elements, that would be quite a problem. And so a windowless detector is not going to have any of that absorption. So it's really good for looking at light elements. The disadvantage being that if you have no window, there is nothing there protecting your crystal. You might get some artifacts, contamination over time. There's also beryllium windows. These were very common for a long time, but they're sort of the opposite. They're really bad at absorbing low energy X-rays because these are pretty thick, but they are very robust. They don't break very easily, which is why they were used for a long time. But we've kind of moved away from beryllium windows, and now a lot of EDS detectors use polymer windows. Namely the ultra thin windows or the atmospheric thin windows are polymer windows. And because they're so thin, they don't absorb too much in the low energy range. In the case of ultra thin windows, they are very fragile and they break easily. So atmospheric thin windows are kind of a compromise where you have this polymer that's supported on a grid. This decreases the effective area, but it helps it so it doesn't break so easily. And it's not so bad at absorbing very light energy X-rays. And this is actually the kind of window that we have currently on all of our EDS detectors here at Nuance. In terms of the sensor, the crystal, there's 2 types of EDS detectors you've probably heard about. The main ones being the SILI detector and the silicon drift detector. So to understand kind of both of these and how they work, you need to know kind of what a semiconductor is. And so if you're just totally unfamiliar, this is your very explain like I'm 5, what is a semiconductor? Your valence electrons are the outermost electrons in an atom. They're usually involved with chemical bonding, but in solids, they can form bands of energies that they can exist in. Electrons in the conduction band can freely move around kind of like as a sea of electrons. And if you apply an electric field, this will pull the electrons and conduct electricity. So in metals, the valence and conduction bands are essentially continuous. It doesn't take a lot to convince a valence electron to sort of drop what it's doing and move to the conduction band. In insulators, the valence electrons are a lot more stubborn, and it takes a lot to get the valence electrons to jump to the conduction band. In semiconductors, it's kind of in between. It is feasible to get those electrons to jump to the conduction band. And depending on the material, or if there are certain impurities or other properties of the material that are manipulated, you can make it even easier. So semiconductors are kind of you're offered a little bit more control, whether you have electrons in the conduction band or not. So in the case of an EDS detector, how does this apply to EDS detectors? So I mentioned that the sensor is a silicon semiconductor. So when an electron, which has negative charge, is excited to the conduction band, it leaves behind a net positive charge where it was in the valence band. So we call this an electron hole pair. In the case of the silicon crystal, it takes about 3.8 electron volts to generate each electron hole pair. So as an example, let's say we have in this diagram, we have a calcium K alpha, which has 3.9 kilo electron volts. If that X-ray hits our silicon crystal, we can kind of easily do the math here. How many electron hole pairs are going to be formed? So we get about 1,000 electrons. And you can easily calculate the charge of this many electrons, the charge of an electron, multiply it. And now we have in coulombs a charge that was generated just from this one X-ray. So this is kind of a simplified way, like we have a direct proportional relationship to the amount of charge we just made and the energy of the X-ray that hit the crystal. So without getting too much into like semiconductor technology, this is a bit simplified, but what's really important is you need this kind of known constant production of electron hole pairs. And it's not necessarily this easy if you can't make sort of an ideal material that you can know that this production rate is constant. Often crystals have impurities or imperfections. And so this is where the Silly detector comes in. This was sort of developed in the 60s. And the process behind this detector was based on the fact that the silicon crystals that they were making had a lot of often boron impurities. And so what they would do is use lithium doping to diffuse into the crystal and basically help balance some of these extra positive holes that were in the silicon semiconductors that they had. The problem is that lithium is highly mobile, it diffuses very easily, there's a lot of noise, and so you need liquid nitrogen to cool a Silly detector. So later we developed the silicon drift detectors, and this is really kind of taken over. You don't see Silly detectors very often anymore. This is sort of the newer generation of EDS detectors are mostly silicon drift detectors. And this was proposed first in the 80s, and this is based on a much higher purity silicon that became easier to fabricate. And it has a unique design with this pattern you see here of nested ring electrodes with a very small central anode on the backside. And these electrodes have varying voltages that can drift the charge after the electron hole pair generation to the central anode. This design allows for a reduced area of the electrodes. It has a small anode, has a smaller path length. It has a much more uniform electric field. And this is all to say you get a lot more counts in less time with less noise, so less cooling is needed. And because it doesn't need to be cooled so much, you can actually afford to make them even bigger, which means even more counts. So now I can hand this off to Nick, who's going to sort of tell you what happens, with cooling and what do we do with that charge that we just generated on our sensor to give us our spectrum in the end.
All right, thank you, Kristen. So that was a lot of information about X-rays and semiconductors and all that. But we still got a lot to cover before we actually get a spectrum that'll help tell us what our sample is made of. So up next, we're going to talk about cooling our detector. Okay, our detector crystal needs to be pretty cold to operate effectively. So the silly detectors typically have, this large liquid nitrogen dewar sticking out of the side of the SEM you might have seen. And the liquid nitrogen is around negative 200 degrees Celsius. And that's actively cooling that little crystal at the end of the rod there. And so this setup's pretty bulky and it uses a lot of liquid nitrogen to keep that crystal cool. So more recently, a lot of facilities have opted to go for the silicon drift detectors, which use a Peltier cooling method. So this is a type of thermoelectric device that's coupled to the sensor by a heat pipe, and that transfers the heat away from the crystal to sort of these fins on the side of the detector body. And that's where it says heat sink over there, where that heat will dissipate. So this helps keep the crystal at around negative 20 degrees Celsius. So here's an example of one of our EDS detectors showing that it's currently cool. So you can see the blue light on the side here is indicating that the crystal is cool. And you can see the fins toward the back of the body as well. All right, moving on. So now our crystal is cool enough to detect all of our X-rays, but we need to turn that signal into something the computer can read. And that's where the preamplifier comes in. So briefly, the preamplifier simply just converts a charge into a voltage signal. All right, so that voltage signal is going to be proportional to the number and the energy of the X-rays detected by the sensor. And the charge slowly builds up on that capacitor in the preamp. So we can see new X-rays hitting that crystal. That's where those stair stepping is coming from in the graph. And once the capacitor is fully saturated, it discharges. So that's that vertical line there. The preamplifier also amplifies the voltage signal in general to just make it more measurable and suitable for further processing and analysis. And that amplified signal is what the pulse processor reads. Although the first thing it does technically is digitize that voltage signal. But after that, it can then remove the noise coming from the sensor and the electronics and all that. All right, so now there's two phases here. So the processor can either be observing or thinking, right? It observes for a certain amount of time to just gather the information, which are sort of these blue areas on the graphs here. And then it thinks about what it just saw for a bit, and it determines the energy of the X-ray that was detected based on the average height of the signal. But during the time that it's thinking, it can't see anything else. And that time that it's thinking is what's known as the dead time. So in general, if your dead time is shorter, you're going to be able to detect more signals, but your spectral resolution is going to be a bit worse because it's not averaging the signal for very long. On the other hand, if your dead time is longer, you're going to get much better spectral resolution, but you'll be limiting how many signals the processor can see. And so you potentially miss certain signals altogether, kind of like this middle one on the right here, just completely was missed. All right, so now that we've got all that, we can put it all together in the multi-channel analyzer. So the resulting energy values from that pulse processor step measurement are then sent to the computer's multi-channel analyzer, which essentially just bins the results into sort of an energy versus intensity histogram, right? And that outputs that onto the display. So you can see a spectra here, and it's clearly got these defined bins at these specific energy levels across the spectrum on the x-axis. All right, and that's all there is to it. So now we have our spectrum that we can analyze. But since we just finished our crash course on our EDS detectors, let's go ahead and take a quick look at some of the EDS detectors that we have here at Nuance. Okay, so all of our detectors here are going to be the Oxford Instruments brand detectors. This kind of just helps keep our processing consistent across all the SEMs and helps keep the data analysis and streamlined. We do have a couple of older generation detectors, which are going to be the Inca detectors on the 3400 and the 4800. They've just got smaller windows, slightly not as good spectral resolution than the newer Xmax and Ultimax detectors. And you can see the 4800 is currently our only silly detector. Okay, but the Xmax series detector is designed to maximize count rates and sort of improve the detection limits for trace elements in your samples. And that one's currently on the 8030. The Ultimax detectors, on the other hand, use what Oxford calls their proprietary extreme electronics technology, which apparently just increases the sensitivity, speed, and resolution. And along with that faster detection, you can also do live chemical imaging on these ones. So you can actively acquire your elemental data sort of in situ as you're scanning, which is super cool. All right, and then this slide here. So the first row is showing you all of the software functionalities that we have for each detector. So like point and ID, layer probe, which sort of gets data from layers of like stacked materials. Line scan, which lets you measure EDS across boundaries and stuff like that. We have just general mapping, large area mapping, and so on. Right? And each of these will let you characterize your samples in different ways. You can really use like the full suite of analysis on your samples here. All right, and then the bottom row is showing all of the additional detectors and attachments that we have on our SEMs. So theoretically, you could use these detectors alongside the EDS detector to get sort of more comprehensive overview of your sample and even some pretty cool in situ data from some of them. Okay, well, hopefully now you have a pretty good idea of which detector might be good for you. But before we finish up, there's just a couple other things that we're going to discuss. All right, so a couple items to consider. One is going to be the detector size versus the solid angle, which you'll see in a second. And then two is going to be the energy resolution of your spectrum. All right, so as you know, the solid angle is going to be the portion of the surface of a sphere that's subtended by an object placed at its center. And you can see from the diagram here that as the detector distance is increased, the solid angle would be decreased, right? So we would lose detecting power essentially. But to maximize that signal, we want to increase that area, which we could also do by increasing the detector size. So in general, a larger detector is going to be better because it captures more signal due to this larger active area. This also is going to help you with lower kV EDS because generally a lower energy beam produces fewer X-rays to begin with. So it can just pick them up more easily. It'll also help you get better spatial and spectral resolution as well. All right, ideally you have a large detector that's positioned, reasonably close to your sample. So those windowless detectors are great for that because they sit much closer to the sample, maybe closer to where the smaller red circle is instead of back here more. And they've actually got a pretty large detector area. So it really covers a lot of the surface of that sphere and gives you great counts and better resolution overall. So if you ever have a chance to use those windowless detectors, they can give you some pretty serious data. Plus they're great for light element detection as well because they don't have that window. All right, and then the other thing we want to consider is going to be the energy resolution. So the energy resolution of your detector is usually measured with the standard of iron 55, which is going to decay into manganese 55. And in that process, it'll release a manganese K alpha X-ray. And then that manganese K alpha peak is how they measure the energy resolution. So ideally, your peaks are as narrow as possible, which is going to help you discern between sort of overlapping peaks. But like many things related to EDS detectors, the resolution is mainly going to be affected by the quality of your sensor. So, minimizing your electronic noise and just other general technological advancements that they're making out there, as well as the detector size and position, like we just discussed. All right, so with all of that, I hope you enjoyed our tech talk on EDS detectors and how they work, and we'll be happy to answer any questions you have. So thank you. And don't forget to register for a virtual EDS training if you're interested.